we're in a period of sensor overload, and the human brain can get overloaded, it gets fatigued, whereas the machine learning can process tons and tons of information and make sense of it.
Welcome to episode 5 of the Zero Pressure podcast series, a relaxed conversation with those on the cutting edge of science and technology. Hosted by me, Helen Sharman, and presented by Imperial College London and Saab. The Zero Pressure podcast series is looking at how science and technology positively can contribute to solving complex, interrelated global challenges of today and tomorrow. Throughout this series, we've been investigating pioneering technologies and speaking to thinkers and doers at the leading edge. Coming up on today's episode about human-machine teaming.
What we are looking for is, one human controlling multiple robots by employing, autonomy and, a very kind of higher level of command and control. I could be right from this room controlling the maritime robotics out at sea across the world. That's the nirvana, if you will.
In a complex system, there are lots of actors, both man, machine, and procedures, and they are interacting with each other non-hierarchically and non-linearly. So this gives rise to a complex system behavior.
Human-machine teaming is ultimately about relationships, albeit relationships with something inanimate. It's the interactions and dependencies between people and machines. Trust becomes a key issue when working with machines, relying on them and extrapolating information they provide. We'll be exploring this and other questions as we look at how human-machine teaming is being used, quite literally from the oceans to the sky, and what it means for air traffic management and the marine environment. But it all comes back to the relative strengths of humans and machines and working out how best they can work together, optimising the capabilities and resource requirements of both. Let me introduce our first guest, Commodore Michael Brasseur. Michael is Commodore of Task Force 59, which is working on rapid integration of uncrewed systems in waters surrounding the Arabian Peninsula. A graduate chemist with postgrad qualifications, including a master's in international relations, Michael was captain of a littoral combat ship and helped launch the NATO Maritime Unmanned Systems Initiative. Michael grew up on an island, and he says, "The ocean makes you happy." Michael, welcome to Zero Pressure.
Well, thank you, Helen. It's very great to be here, and Zero Pressure makes me happy as well. So looking forward to the conversation.
I like that. Thank you. Now, I know chemists get into all sorts of interesting places. I mean, I too studied chemistry, and I can imagine the attraction of traveling the high seas. But do you still manage to get out on the water in your new role?
Absolutely. In fact, I was out on the water this past week. Our new task force did our first operations in the Arabian Gulf. Quite an enjoyable experience to be out on the water. And even better, it was Taco Tuesday. So we were out on a Coast Guard cutter, and the chef was fantastic. Shrimp, chicken, and steak tacos. It doesn't get any better than that. Robots, the sea, and tacos.
So this is what makes you most happy. So long as you've got robots on the sea and some good food, you're good to go. But tell us what you've been using, particularly uncrewed vessels in the sea to do.
So we've gotten a series of maritime robotics above, on, and below the water. And we're just we're essentially burning them in right now. We're teaming with our crews, building trust in the human and the machine, between the human and the machine. And so we've just been running them through their paces. Ultimately, we'll put them on missions, a whole host of missions here in the region, whether it's, counter piracy, maritime interdiction operations. There's a bunch of uses for maritime robotics. And so, but at this early stages, we are just building trust between the humans and the machines.
Building trust is a sort of an interesting word to use, I think, when we're talking about machines, because we often talk about trusted with humans, obviously, and I can also imagine with animals. But how does it work when you're trying to build trust then with machines?
Well, Helen, I think you probably can relate to this well with your space adventures. But there's there's a connection between the human and machine, and there's a level of understanding that needs to develop that the machine will do what we expect it to do when we expect it to do it. And, depending on the level of autonomy involved, it could be algorithms driving the machine to do what we thought it would do, but it does something else. There's also a lot of value in leveraging autonomy to reduce the cognitive load on the watchstander, on the decision maker. We're in a period of sensor overload, and the human brain can get overloaded, it gets fatigued, whereas the machine learning can process tons and tons of information and make sense of it. Okay, so I think those kind of autonomies are very good use there. For example, we have some USVs that go very, very fast, and fast enough that the human, if it was on board, probably couldn't withstand kind of the beating of the ocean. So this is a case where the human was the limiting factor in the teaming effort. So that's another case where we wouldn't want the human to be the limiting factor when employing, a maritime robotic. So as an operator, it's a matter of just understanding the limits of the machines, understanding the reliability, and then, depending on what level of autonomy, understanding perhaps we, may have programmed something wrong. So there's a period of kind of shakedown that we're walking through right now before we would put something on a real mission.
So I totally get if you've got perhaps a complex machine and you're familiar with it. So yes, like a spacecraft, as you mentioned, and I guess perhaps even a boat is similar. But you can kind of sense what it's doing. You hear it creaking because one side might be warming up. You can feel a vibration or hear that vibration because a pump might be working or something. So you kind of know what's happening because it's happening around you. But if you've got a vessel that's not got any humans in it or even on it, that must somehow be a bit more difficult you're taking in information that is not really in the same way that humans naturally perceive somehow.
Helen, you're exactly right, because you mentioned I was this captain of a littoral combat ship. The ship itself had 8,300 sensors on it, and was supposed to give us alerts, if something was about to fail or, the engine was about to go down. But do you want to know probably the three best sensors? It was, my ears, my nose, and, the touch, of the machine. So you bring up a very, very good point. When the human is removed from the machine, you disconnect, and that sixth sense, if you will, is not there. So I think what we're talking about here is in the space that we're operating in, can we rely on the machine to do what we're expecting it to do? For example, we certainly wouldn't want one of our uncrewed machines to violate somebody else's territorial waters. That we wouldn't want that to happen to us, so we wouldn't want our machine to do that to them. We also need to understand how they'll react when people or potential adversaries try and disrupt what we're trying to do, whether impact our communications or GPS or whatever. So it's a really difficult problem. The only way you build the trust is by operating in a comms contested environment, by going through the paces, by doing several exercises where the machine is doing as it's been designed to do.
So it's that repeatability so you're expecting it to do something and it does, but I suppose oftentimes you're asking it to give you information that you don't know, which is why it's going off in the first place, to find out information. So how can you trust that this new data, I suppose, new information is, the data are new, that they are right, they are verified, they're accurate?
Yeah, so this is another point that, as I'll go back to the other example with the 8,300 sensors on the LCS, at some point, if the sensor is giving you bad data, makes you question the other 8,299 sensors, And so I think the way you achieve that is by getting mass of sensors in the water. You can certainly leverage some AI and machine learning tools to help do the analysis where it can determine, okay, that's an anomaly, that's not normal. And that's part of the value proposition that we're putting out. The maritime robotics are much less expensive than destroyers and cruisers, and there's a quality and quantity. So there's value in getting more sensors out on the water to enhance our maritime domain awareness.
You talked about teaming with the machines with the humans. Now, if we think about teaming humans with humans, we're thinking about perhaps their psychology sometimes. So yes, I'm thinking about a space mission. You're thinking about who works best with whom, and making sure that they've got different kind of skills to bring to that team. So what kind of issues, they must be different, but what kind of issues are you thinking when you're teaming a machine with a human? I mean, do all machines work well with all humans, for instance?
The thing that is most important for this to be successful is that user interface. So I'll give you an example. We did some operations this week, and we were in this particular operation, we were in piloting mode. We had some unmanned surface vessels. The vessels themselves are capable of, being piloted. They're capable of being semi-autonomous and then full autonomy. Well, we were in the early stages, and we were using the piloted version. Well, it just so happens that the user interface was an Xbox controller, which is brilliant for the generation of operators that are, that are going to operate these. They play on their Xbox, right? Now, if it was an Atari controller, I'm dating myself here, that might have been an issue, but it was an Xbox controller. That user interface is seamless. It makes the transition really, really easy to operate. I operated it myself, and I had very little training on it, and the machine did what I told it to do.
What interface do you like to use best? So you talked about an Xbox controller, which is sort of a manual, but are you getting visual input, so very much like sort of watching a screen and then using that? Is it? Do we use also hearing? Are there other senses involved?
Yeah. So for this particular exercise this week, which was the first stage, was out on the water. The feedback loop was us, the human, sensing it, controlling it, and watching it. That's good to start, but not sustainable. What we are looking for is, one human controlling multiple robots by employing, autonomy and, a very kind of higher level of command and control. So in that interface, I could be right from this room controlling the maritime robotics out at sea across the world. That's the nirvana, if you will, and again, it gets us the opportunity to get the quantity to really get after some of the problems and enhancing our maritime domain awareness. I was struck by an example a colleague of mine said about, we were landing an unmanned aerial vehicle on an LCS, as a matter of fact. The unmanned aerial vehicle required 12 people, to launch and recover, on a certified flight deck, which kind of defeats the purpose of the uncrewed vessel. So we want that kind of inversed, where one person is controlling 12 or 13 maritime robotics in all domains above, on, and below the water, and then getting the feedback in a comprehensive manner that feeds in years and years of data so that a pattern of life can be developed, and then we can determine when something is not in the pattern of life, when something's abnormal. That would be highlighted for the operator to take a closer look at that, maybe dial in on the sensor on that particular maritime robotic or satellite. And we're looking at, unmanned systems from seabed to space.
Before we go back and go to space, though, I think, which is another whoa for me, I think this idea of one person operating a whole load of different machines, I'm just starting to think how that actually happens in practice. I guess one person has to be a little bit sort of multitasking and aware of lots of different inputs. Are we just really trying to get the machines there to be more autonomous in the first place to allow that to happen?
Yes, that's the aim, Helen. And that's, we're going to have a couple of projects here in one of the most challenging environments in the world to operate. We operate in the Red Sea, the Gulf of Aden, the Northern Arabian Sea, the Arabian Gulf. So this is a very, very challenging environment to operate. It's hot. It's a problem-rich environment. It's salty, it's sandy, it's windy. It's a good place to live, though, over here. It's really good. But this is what we're working on. That's what we're building towards. We're working on a few prototypes that will determine if that's possible, and if it's possible on a small scale, how would you scale it, across the AOR?
So let's go back to that bit you mentioned about space. So are we talking about satellites passing on information? Is that the idea? So you can then have robots all around the world using the satellites to beam that information to wherever that controller is. Is that what you mean by the use of space?
Yeah, I'm looking at satellites as just an additional sensor, that are providing persistent surveillance. It's an important piece of the entire concept. And the concept we're talking about is called a digital ocean. So which would bring all this together from seabed to space.
Ooh, that sounds like a digital sort of world plus what's out there in low Earth orbit, or perhaps higher than low Earth orbit as well, though. So tell me a bit more about a digital ocean. So we've got satellites, which are obviously giving you information. We've got vessels on the surface of the sea, which are giving you information. Presumably there's stuff, did you mention under the water as well? How does that combine to make a digital ocean?
So basically a digital ocean, this is a concept that we've been working on with NATO, and I co-chair an innovation advisory board at NATO. But we've been kicking around this idea. It's not a novel idea. It's just we've been developing it pretty comprehensively, where you would leverage existing assets. So whether that's ships, submarines, airplanes, whatever's out there, sonars, radars. So leverage existing assets, incorporate new maritime robotics above, on, and below the water. Again, taking those feeds. Could even be, buoys. We're teaming with DARPA on a really exciting project using buoys. It's just a matter of getting a lot of sensors in the water, essentially digitizing the oceans and getting it in a digital format that's usable and ready to be exploited with machine learning and an AI. So this sort of exploitation can have a ton of different applications. There's certainly military applications to what we would be doing. So would we be looking for illegal fishing, illicit shipment of weapons? On the high end, you could probably use it to find submarines. But there's also a huge amount of research, the type of work that Imperial and other great universities do on climate. The oceans are critical to solving our climate concerns. So it's about amassing the data and then preparing it in a manner that's usable for machine learning and AI to get in the predictive state.
Lots of different levels of autonomy you've mentioned. Are there some situations that you think machines, absolutely, we definitely want machines to do because that will make humans safer, for instance? And are there some things that absolutely humans will always be doing or should always be doing?
There's certain things, very, very dangerous, high risk operations that perhaps you'd want to put a machine in to do it first, to get a critical piece of information or deliver some effect that would change the outcome of the event. Now, when you talk about killer robots and this sort of stuff where the where the robot is making a decision to kill, I'm not there. We'll always keep a human in the loop. And, we have some pretty high standards in that respect.
Michael, thank you. We'll come back to you shortly. Michael there was talking about humans having sensor overload when there's just too much input. It's about quality and quantity, he said, optimising what works best for the machine and the human. Here's a reminder that you can submit comments and questions via our podcast Twitter @ZeroPressurePod. We're keen to hear from you and may even feature your questions in the next episode, so please do get in touch. Now from the oceans to the air, let's think about quite a different application of human-machine teaming from military operations in the sea to explore how air traffic controllers and airlines are using human-machine teaming to coordinate and manage traffic in the skies. Our second guest is Professor Samir Alam. Samir is the Deputy Director of the Air Traffic Management Research Institute and Co-Director of the Saab NTU Joint Research Lab in Singapore, a mathematician turned computer scientist. He's over 20 years' experience in the design and development of artificial intelligence and machine learning models for air traffic management and airport operations. Welcome, Samir, to Zero Pressure.
Thank you, Helen. Thank you for having me. It's a great pleasure to be in the company of such great personalities. Thank you for having me.
Tell us about how human-machine teaming is playing a role in air traffic management.
Oh, the role is, I would say, very complementary. Why? Because air traffic management, as you can imagine, is not a straightforward system. It's a complex system. And a key differentiator for a complex system is the behavior is not observable. It emerges from the interaction of the subsystems. So that's why air traffic control operates on the edge of chaos. It transitions between orderliness and disorderliness based on small perturbations in the system.
Okay, so getting the picture, you said on the edge of chaos, which sounded terribly exciting and also terribly worrying in some respects. Is it only chaotic because we don't fully understand the causal implications of one thing on another? Or is it really is it chaos because it really is? Nothing really can there is apparently no real cause for a lot of these things.
Very interesting. It's edge of chaos. It's still not transition into chaos. So it's edge of chaos right there. And human beings with their inbuilt intelligence, causal mechanisms, are able to maintain the system in this fine state. And as I mentioned to you, because of the inherent feature of a complexity, in the complex system, not only there are many entities, but these entities may have conflicting objectives as well. Airlines want to minimize their fuel burn, but air navigation service provider want to have a safety, right? So there are always conflicting objectives. So in a complex system, there are lots of actors, both man, machine, and procedures, and they are interacting with each other non-hierarchically and non-linearly. So this gives rise to a complex system behavior. And all these entities, right, be it military, civil air traffic, or meteorologists or air navigation service provider, they all are actors and they have their own criteria to satisfy. And they all are, interacting through these complex man-made procedures in order to achieve a higher level system objectives.
Humans are quite good at negotiating who's going to take or whose decision should take precedence, let's say. So for a potential collision, I can imagine, and one aircraft is allowed to continue and another one is advised to move away. If you've got a machine, won't they all be trying to save themselves? They all want to make sure that their way wins. So how do machines negotiate like that between them?
So negotiation protocols among the agent, when they collaborate and cooperate with each other, is a open research question when it comes to collaborative AI. See, now in the complex system, as I mentioned to you, there's not one agent. There's not one system. There are multiple systems. All have their AI agents, right? We cannot just have one system with the AI agent and another system with human. It will not work. All systems have to have some form of digitality. Just like Michael has just mentioned, digital ocean, we need to have a digital airspace, where all entities are able to cooperate, negotiate, and exchange information for decision-making and for situation awareness. And that is the time when multiple agents cooperate and collaborate with each other. These research questions that I mentioned to you just before that, how that they can coordinate or communicate with each another to agree on a shared strategy for problem solving. Right. So this is an open research question, open problem, and one of the research that we are doing at the moment is based on extended arrival manager. See, the terminal airspace. The terminal airspace is one of the most congested airspace in air traffic, which is around the airport because everybody is coming to land. Correct. That's why you have so many holding stacks happening. 20 minutes aircraft is under hold. Right? How about if we can predict this holding pattern, if we can predict this delay and can absorb this delay instead of transition into the cruise phase of the flight. If we do that, we have to apply some speed control strategy. So aircraft can slow down within their parameter, some can become faster, and this way they arrive in the transition airspace at the right time. But who is going to absorb the speed? Who is going to get faster? This is the time when cooperative and collaborative AI agents come into the picture. They take consideration of all these aircrafts that need to negotiate with each other to find the right balance of speed management so that they can absorb the delay in the transition airspace and avoid holding and delays and fuel burn, of course. So the key challenges, I think some of them already have been mentioned by Commander Michael here, that when we talk about such collaborative system, right, we ask the question that how can AI agents learn to recognize someone's intent? Okay, i.e. human here. How can an AI agent learn what behaviors are helpful when working towards a common goal? When I say working towards a common goal, common with goal with a human being. And how can they coordinate or communicate the agents with another agent, being a human or an agent, to agree on a shared strategy for problem solving?
Sorry, Samir. So when you say an AI agent, you mean a machine, essentially. You don't mean somebody operating the machine necessarily.
It's an agent we can imagine as a software program, which has perceptions, which has sensors, and which can take action. This is the basic definition of an artificial intelligence agent. An agent operates in an environment. It perceives the environment. It builds the situation awareness. It can take action and can also evaluate the repercussions of its own action. What you do now may impact the outcome 30 actions later. These things are not possible to write a hard code program with a set of rules. Not possible. That's where machine learning comes into the picture. And secondly, I think Michael also touched on that very well, that this is also what we call as adversarial learning. See, the foxes wouldn't have been that fast if rabbit wouldn't have been running that fast. So this is called as competitive coevolution in nature. The rabbits are becoming faster and the foxes are also running faster. Foxes eat those rabbits that are not fast, so they do not grow up, do not mate, and they do not actually bring those fast running traits to the next generation. What we do here is the algorithm plays the role of adversary, that is red teaming, and human plays the role of the blue team, right? An algorithm keeps on bringing more and more challenges to the air traffic controller. Okay, you solve this conflict, let me bring a more complex. Let me bring a conflict from this side. So this way, the machine is becoming intelligent, learning from the human that how human would have handled such a complex scenario. So this is the cutting edge of research in AI and machine learning, adversarial learning, cooperative and competitive co-evolution to design the system which are trustworthy and explainable. So, but if a system has learned from the air traffic controller past behaviors and actions, there's a very high chance that the controller can rely or can trust such an autonomous system. So learning from the human behavior and the pattern and bringing AI to create a symbiosis of the two is what is the cutting edge now.
But do all air traffic controllers operate in the same way? So, for instance, if a machine learns from me, let's say I suddenly managed to train myself up to be an air traffic controller, I would then teach the machine to learn what the decisions that I would have made. Would somebody else be able to use my machine? Could I use somebody else's machine?
So all the air traffic controller, first of all, undergoes the same training by IQ, all of them. right? However, over the time, based on their unique sector that they are working on, they develop a specific bias or specific mechanism. Still, it is safe, right? So what we are looking at as a personalized autonomous system. When a controller loads himself into a given scenario, the machine will load specific agent which understand the bias and the behavior of those air traffic controller, so that these machine learning algorithms can help them to maintain their cognitive complexity. Remember, an air traffic controller can maximum manage 18 to 20 aircraft, not more than that in a sector. This is the cognitive limit, right? However, if we let machine learning algorithms take off this cognitive limit a little bit into its own hand, then we can bring 30 aircraft into a sector, which means that the airspace capacity can be significantly improved. Safety can be significantly improved. Air traffic controller do not wait for two aircraft to come into a loss of separation, right? It will not wait that two aircraft came to each other close 5 nautical miles, 1,000 feet separation, and then do the configuration. No, they are they are choreographing the traffic before it enters their own sector. They are playing lots of scenarios in their mind that this might can go wrong. That's the reason I am flowing the traffic this way. So this is the cognitive capability that we want to
But
be given
so
to
your
the air traffic
machines learn
controller.
from a human, but we've talked about a human. You must use more than one human. How do you choose which people the machines are going to be learning from? And then can all the other humans, does everybody feel that is as they would have decided?
So Helen, you hike a lot, I think, right?
Yeah, I love walking. Yeah.
You are a hiker, and I'll give you an example from the same context. So when we are going through a jungle, a very thick jungle, right? And we don't know how to cross through that. And here we have a very fantastic technology with LIDAR and GPS and algorithms for shortest path finding, and it gives you on your screen a particular complex way that takes you through the jungle. But hey, stop. You suddenly see a path already trodden, right? The woods are lovely, dark and deep, but I have promises to keep and miles to go before I sleep. So I see that trodden path. Those trodden path people have taken before. So how about this machine learning algorithm? Can't it take that knowledge also while giving the solution to me? If there are many people have taken that particular path, it would have become more trodden, more reinforced that we call it. For the people who have taken other path, they didn't come back, so their path didn't get reinforced, right? So this particular path which people have taken to go through the jungle is the human intelligence which machine learning algorithm should take into consideration. So we are moving from symbolic AI to machine learning. In that sense, we collect the data and use the data and make it hybrid with the knowledge that we have about the environment. This makes these algorithms very powerful because now they are taking a collective human knowledge that has evolved over time. See, air traffic control is there since 1960. So over 60, 70 years, we have collected a lot of knowledge. We have thousands and thousands of hours of transcript tapes. We have thousands and thousands of hours of radar data, right? This is a very valuable information which can be mined, patterns can be learned, and can be used by machine to advise human beings.
What's the interface then between the human and all of this information? Again, I'm wondering about, is it just visual? But you're talking about if an air traffic controller would be actually giving speech commands or speech requests, perhaps to a pilot.
That's a good question. And it actually touches on the state-of-the-art research in artificial intelligence, which we call as explainable AI. In explainable AI, machine not only advise you the decision, but advise you the logic behind the decision. And this logic, when it advises the human being, is in an understandable way. So at the Saab NTU Joint Lab, we are experimenting with the AR and VR technique, augmented reality and virtual reality technique. For example, using HoloLens and air traffic controller can work from home. No need to come to the air traffic control center. Sit at home, put on your HoloLens, the machine learning algorithm loads your preferences, your particular airport that you are managing, and then when using the human embodied gesture like pinch, tap, double tap, and stretch, you can manage the entire airport airside air traffic control. So these are the experiment we concluded last month with the 16 air traffic controllers actually, and we loaded several scenarios. We did this research. We published the paper in one of the top scientist conferences to demonstrate that the next generation of air traffic control system can be only enabled with the next generation of interfaces, which are based on augmented reality and virtual reality. Not only to use them, but also the machine learning algorithms have to be sufficiently intelligent in the sense they just don't tell you do this, do that. No, they will tell what to do, how to do, and also what is the reason behind doing that.
Samir, thank you. It's so much to think about. Samir made some very interesting points. He highlighted the competing objectives of airlines and traffic controllers and how they need to work together as part of a larger, complex system to arrive at a shared strategy for problem solving. And he explored how artificial intelligence continues to develop in his world. Samir used some wonderful metaphors to describe how AI agents learn and how collective human knowledge can sometimes give a better resolution than data acquired in other ways. Samir shone a spotlight on how AI systems are interfacing with humans to provide usable information to air traffic controllers with state-of-the-art virtual and augmented reality technology. So let's come back to both of our guests now. The natural world is complex and interrelated. I mean, Samir's eloquently told us how many different aspects of air traffic control there are, and of course, Michael, we're dealing with so many different machines from space to underwater. I mean, is it now a question of just allowing our machines to learn off each other, or is it just a sort of a communications thing? Do the machines just have to communicate together? How are we going to really develop this? I mean, Michael, do you want to start off with that one?
Yeah, first of all, this notion of the environment, what we kind of experience in the maritime environment is, a lot of this technology started over land, and when you get it into the maritime, it's a very, very challenging environment, and it doesn't always transition. So a lot of the drones that you're talking about, they may work for fine over London, but not over the Arabian Sea. So the environment matters, and it doesn't always transition easily. Yeah, I agree that there. It was kind of the point I was getting to about the quality and the quantity. So by getting a lot more sensors out in the environment, we can get the data sets that are necessary to understand it more comprehensively. And we have to get the sensors in the water and learn from what they're trying to tell us. And we've got to get it, in mass.
If the drones are going to have to talk to each other, so I'm guessing there are places, perhaps particularly underwater, so where you can't get that information back to tell them to do something else. So can they learn from each other? So let's say you send a drone off to find some information out, and yet actually having it, let's say it wants to take the temperature of a certain part of the ocean, but it's past another drone that's actually got a very, very weird temperature measurement. And so some more investigation needs to be done on that. But you don't know yet until you've got the information back. So Michael, can they be talking to each other? Can they learn off each other in that respect?
Yes, absolutely. And I mean, that's kind of the next level of discovery, the next boundary that we're pushing through. It's a bit more challenging underwater, but not unachievable. And there's been some significant advances in this space. So yes, the answer is yes.
Are we going to be able to take one context to another? So if Samir's got all this wonderful information that's from the air traffic controllers, could that be taken and used in a marine context? Or is it just too different, do you think?
So this is an area in machine learning that is now being researched a lot of transfer learning. In transfer learning, not only we can transfer the knowledge learned from one domain to another domain, but also we can just do an incremental learning. So we do not have to learn from the scratch. If we are developing a machine learning algorithm, let's say to navigate a nuclear powered submarine into the depth of the ocean, the knowledge learned by running a diesel-powered submarine, for example, here can then be incrementally used in such a sophisticated system. So transfer learning is an area which is of growing interest, and I think it's a way to go so that the enormous time that's spent in training the machine learning algorithms on zillions and millions of terabyte of data, we don't have to go through that cycle again. So as a child, we came preloaded with some knowledge, right? So we don't have to build things up from the scratch. A child with intuitively knows and understands some things. So this is the mechanism of transfer learning to enable next generation of algorithms which have some embedded knowledge, a generic knowledge already there. Sorry, Michael, you were there. Go ahead.
No, I just was going to agree with Samir. I think that there's a lot of transferability, between domains, whether it's sea, space, land, air, and the cyber domain. So I think there's a bunch of transferability. I think what's different is just the physical side of it and how the actual machines operate in those different environments. And that's what I was kind of alluding to. The sea can be very, very unforgiving, and the machines don't always perform the way you would expect in the sea.
So scaling up. So we're already talked about. You mentioned, Samir, the sort of almost on the edge of chaos. There's so many, so many different factors out there. And Michael's mentioned lots of different machines working together. Is this what's termed swarming? Could you use swarms, Samir?
Yeah, swarm intelligence is one of my PhD was in swarm intelligence for air traffic control, actually. Oh. So swarm intelligence is the area that I worked a lot. So my first research paper was titled "Ants Guide Future Pilots." So by using the concept of ant colony optimization, a swarm of ants, how those ants can help air traffic controller to come up with most optimal routes that can take an aircraft through a thunderstorm or through how they can avoid bad weather situation. So swarm intelligence, which is again coming from the collective intelligence of small agents, which doesn't have their own intelligence, but the intelligence come from the interaction among themselves. So that is the collective intelligence. So
yeah. So I guess to Samir, to what end is the value of the swarm? I mean,
it is robustness and collective decision making. This is the power of the swarm. Robustness and collective decision making. Right? You have 50 drones. Every drone can only scan a particular area of the sea. Some drones are good in communication, some are navigation, and some are good in surveillance. And they act as swarms to go into the high sea to rescue or to manage a hijack situation. This can be only done by swarm intelligence algorithm. No single drone can achieve that. And these swarms can be inexpensive drones which cooperate and coordinate with each other. Some, even if they are shot down or they malfunction, no problem. So swarm intelligence, especially in the area where the operations are not so conducive for human beings, the swarm intelligence or collective behavior is very important. Even like a Mars rover, right? Eventually, we will see a swarm of rovers scanning the Mars surface by the collective intelligence of each other.
But I was interested in how humans interact with swarms. So do we interact with a swarm in a different way than we would interact with a single machine?
Okay, so this question is answered by one of my research or PhD student who is working in shepherding algorithm. So have you seen a shepherd? Shepherd has a dog, and a dog has 50 sheep that it can manage, right? This is the exact concept that we are working on. Human, instead of a dog, we have an AI agent, right? And this AI agent is managing 50 to 60 small operations. Just the way a smart dog can manage all these sheep with just an idea from his owner. This is the same shepherding algorithm that we are developing for drone management system.
Does that translate to a maritime environment, Michael?
Well, so I love how Samir brings these very, very complex ideas to life, through kind of human, kind of organic animal experiences.
Thank you both, Samir and Michael, for sharing your insights and experiences with us. It's been utterly fascinating. I can see there's still so much more for us to learn about human-machine teaming and how humans and machines best can work together. Thank you.
Thank you, Helen. The pleasure is all mine.
And thank you, Helen. It was a great conversation. I learned so much from you and Samir and really enjoyed the conversation. So thank you for inviting me.
And thank you for listening and joining us on this podcast journey, which has taken us from the deep oceans up into the skies and beyond. If this conversation about human-machine teaming has got you thinking and you'd like to ask me or our guests any questions, please do reach out to us on Twitter at ZeroPressurePod. We may feature your questions in the next episode, which will examine the new space economy. Now, this question is from our last discussion on developments in quantum computing. This question here is, where do you see quantum computers being used? Well, personally, I can see that to rival the capability of classical supercomputers, quantum computers will need to use many more qubits than they do at the moment, and getting to that sort of level without too many errors in the system is likely to require a large and complex piece of engineering that's only sensibly available to most of us via the cloud. But I reckon that quantum computers with only a few qubits will become integrated somehow with computer electronics, not necessarily to give us a novel capability, but to allow the same computing power in a smaller space or using less energy. And we'll use quantum alongside classical computers in many settings. So I think quantum computing will gradually grow on us. I can't believe that humans won't creatively engineer capability to use quantum computing in places we're not actually targeting at the moment, as we develop the science and engineering to do something transformational. So if, surely when, they start to become practical, that's a game changer. And if you missed the discussion on that or want to know more, then do listen to the previous episode. I look forward to hearing from you and to our next discussion, so please do get in touch. In the meantime, I leave you with the words of Alan Turing. Machines take me by surprise with great frequency.